Okay. So just to start, we're just going to do a little quick review about what we went over last time. So again, we're still working with palindromic numbers. And what palindromic numbers are just numbers that read the same forwards as they do backwards. Now with this, we did a couple examples and word problems where we found how many palindromic numbers there were in between two different numbers. We went over another example where we were trying to find a bib number, so the next palindromic numbers and so forth. And another thing that we went ahead and discussed last session was talking about perfect square palindromic numbers. And a lot of that was when we did 11 squared, 101 squared, 1001 squared. We saw that the number for 11 squared was 121. The number for 101 squared was 10,201. We noticed that the base of that number, so we'll go back to it in a second here. So let's go back into our example. So we noticed that the base in our number, if there were no zeros in the base of our number, then there's no zeros in our answer. If there was 1 0 in the base of our number, then there was going to be 1 0 in between each of the digits in our answer. So a lot of different things that we were working on is just the patterns of the 11 squares and then also 11 cubes, right? Should have went back a little further, and that's all we were kind of doing. And then we did a couple fun examples where, instead of doing 11 cubed, we were going backwards and finding cube roots and fourth roots. And then what we did also discuss is that a lot of the patterns that you notice here are going to be reflected in the Pascal's triangle, which we will talk a little bit about Pascal's triangle in a couple slides. So what we'll go ahead and kick off for today is one beautiful word problem. How many of you like word problems? Yeah, a couple. How many of you don't? It's okay. Not me, okay. Definitely word problems were not my favorite growing up either. Okay. All right, so here we're gonna start. We know that Sachin plays for the Orlando Quidditch team, and he made sure that he picked out a jersey number that was a palindrome, right? So a palindrome just means that it's the same forwards as it is backwards. So Quidditch rules state that his jersey number has to be less than 1,000, and he needs to choose an even number where the product of those digits is 12. We need to figure out what is Sachin's jersey number. Now, keep in mind, and I know I already got some answers here. Keep in mind that the product of the digits of this number have to be 12. So I know this is definitely a multi-part type of problem, but make sure you're reading each part carefully. And also make sure that if you haven't been able to message me, there are 2 other GTAs here, Alexander and Connor, that you can message also. They are also able to call on anyone that, message them also. You can talk to them about questions and, anything you have regarding the material and fun stuff too, right? We'll give it a couple more minutes in case anyone is still thinking. I got a couple different answers. How about you guys? Alex, Connor, what you got so far? A couple different?
No one's messaged me. I don't
Oh,
know if
no.
y'all don't like me anymore.
All left out.
Same here.
Oh. Are they able to message you?
They should be able to. They should be able to message any of the hosts.
Okay, someone messaged me, so.
There you go.
Okay. Someone said explicitly they're still thinking. So if one person says it, should probably.
It's definitely not the easiest problem. We definitely had I guess we're going a step forward from what we did last 2 sessions.
And I also have one of these, and this is a good thing. I have one of these where if one word in this question was different, the answer would be correct. Okay.
I know it's not the easiest problem, so we'll give it a little bit more time in case anyone's still going ahead and thinking about it. All right, so we definitely got a couple answers. Should we go off and kick into the answers?
So do you want me to call on someone who gave me an answer I think is interesting? Okay, so Shirley Donoso, would you like to share your answer and how you got it?
Yeah. Oh, so I got 66, but I just realized it said product. So yeah.
Cool. Yeah. So that's perfect because if the question had said sum, then you'd be good. That meets all the conditions because 66, 6 plus 6, that would be 12, but we want the product. So yeah, that was the one I was thinking of. Also have Arman Sadri. Would you like to share your answer and what your thinking was?
So what I got was 2, 3, 4, or 6 because they are all palindromic, and you can multiply them to get 12, which is also the number that
it seems I have to listen closely to him because like his voice isn't that loud.
I'll repeat what he said. So he got that it could be 2, 3, 4, 6, and the reason I asked was because I wanted to hear what the reasoning was. And so the reasoning was because I can multiply some of those to get 12. So 2 times 6 is 12 and 3 by 4 is 12. So here, the reason I wanted to point this out is it's a word problem issue, right? In the one number that Sachin has on his jersey, the digits of that number, the whole number, you take the digits and multiply them together to get 12. So 2, 3, 4, 6, you're right, single digits happen to be palindromes, but when it says that the product of the digits in his number is 12, it doesn't mean that the product of the possible answers is 12. It means for this specific number, you want the product of the digits to be 12. So that's why I wanted to point that one out for being careful with the word problems. And then that's actually all I got. If Connor wants to share any, or Maria wants to call on someone, or if anyone has questions on anything said so far.
And also keep in mind, we do need an even number, right? So 3 wouldn't be even.
Good point. I didn't even think to point that out.
All right, so I'm gonna go ahead and call on, whoops. Not the best with this mouse, but let me see. Ethan, you wanna share what you did and how, what'd you get?
I got 232
How'd you get that?
because it's less than 1,000. Well, how I got it is I first found the product of 12. So you could either do 2 and 6 or 3 and 4. So with 2 times 6, you can break that into 2 times 3 times 2. And then you would get 232.
By just rearranging it so it's a palindrome. Nice.
Yeah. I was definitely a smart way to think about it. Did anyone get the same number and do it differently or get a different answer? This was the answer that Ethan got. Did anyone do it differently? No? Well, this was definitely, oh, somebody was talking. Go ahead.
Well, it was me, and I was just going to comment to everyone else. Keep in mind that sometimes you might intuitively see just, oh, here, you might just stumble on it and be like, oh yeah, that works. But remember, what you really are interested in is not the number, but the way you thought about getting the number. And I'll let Maria go into that. But remember, that's what you really want to focus on.
And that was kind of part of what I did. I definitely did a lot more work for this problem than Ethan did. So it was kind of quick that you saw that. So congrats on that. What I went ahead and did first was just list the factors, right? So factors of 12 are simply 1, 2, 3, 4, 6, and 12. So I do know that since I have these are factors, these are the numbers that I can multiply together to get 12. But since we're thinking of just the digits themselves, I'm going to take out 12 because 12 is not just one digit, it's 2. So I want to be looking at the digits that I can use, which are 1, 2, 3, 4, or 6. We know 0 can't be a digit because the product of 0 times any number would be 0, not 12. And since the first and last digit have to be the same, if I was to choose, let's say, either one of these, 1 times 1, that would be 1. 2 times 2 would be 4. 3 times 3 would be 6. 4 times 4 would be 16. And 6 times 6 would be 36. So I can't use any of these digits twice, nor can I use them just once, right? Because it's not going to give me the product of 12. So I can have some digit, let's call it n, in between two other digits, right? And what we could do is we could test it out. If I did 6 and 6 as a digit, then n has to be some number. But I already know that this won't work because 6 times 6 is 36, which is far greater than the product of 12, right? So I would get 36n, which is going to not get me that 12. Another one I can go ahead and try is 4 times n times 4. And keep in mind, I'm choosing 6, 4, not 3, because 3 is not even. And I would be choosing also 2 to test which ones I can get. So 4 times 4 is 16, so 16n. Right here, it's not going to be a product of 12. It's going to be larger, right? So that's not going to work. But 2 times 2, that's 4n. 4n, I can multiply something to 4 to make 12. So that I can work with, right? Now, if we were to think about what products 4 times what makes 12, well, I know that n would have to be 3. Such that if our n is 3, then we have 4 times 3, which is 12. So that means my number would be 2n, which is 3, 2. Anyone have any questions about that? No, yes, no.
Does anyone have any comments on it? How does it make you feel? Do you feel like that was a good question? That was a stupid question?
Sounds interesting.
Interesting. Yeah.
Okay, good.
What else are we thinking about this problem? Feel like we could do all the palindromic numbers now? All the word problems that we get? Yeah? Okay. Well, let's move forward. And it is kind of very confusing question sometimes, especially since there's multiple things that they're asking. So we're going to go into a topic called triangular numbers. Now let's consider this pattern. We have a pattern here with 1 dot, 3 dots, and so forth. What is the rule of this pattern? Can anyone tell me?
Well, let's see. It's starting at 1, then it's 3. 1, 2, 3, 4, 5, 6.
You have 1, you have 3. How many in here?
4.
How
Like,
many dots?
How many dots? 6.
How many in the other one?
10. Let's see.
Okay. I notice Armand has a hand raised digitally. Go ahead.
Well, I thought something. Oh, whoops.
What do you
Microphone
think?
volume is a bit loud.
You're good.
Oh, you're good.
All right. What I thought is, looking at the pattern, if you notice the bottom, like the bottom of the triangle, you can see it's going from 1 to 2 to 3 to 4, but that was just a comment.
Okay, but that's a good comment. That actually is heading in the direction we're looking for.
Anyone else want to take a try? You someone I haven't heard from today? Clayton, you want to go ahead and share?
So if you look at it, whatever the thing was, as soon as it goes to the next one, it adds another dot or whatever in size and then puts it under it. So the 1 point becomes the top point and then it adds 2 under it. That triangle becomes the top piece and then adds 3 under it. And then that becomes the top piece and adds 4 under it. And then eventually 5, then 6, then 7, then 8, and so on and so forth.
That's a really good observation. All right, so when we talk about these triangular numbers, the actual sequence of the number of dots from each triangle is actually called the triangular number sequence. So here we're going to actually discuss a particular pattern. So just as we were counting our dots, right? These numbers are going to be part of our triangular number sequence. So the numbers will be 1, 3, 6, 10, and so forth. And we can see a lot of these patterns in something we call Pascal's triangle, which we talked about a little bit last time, and some of you were asking more questions about Pascal and his triangle. How many of you are familiar with Pascal's triangle? How many of you are not? Some are, okay. Well, here with Pascal's triangle, as we mentioned last time, from this sequence, and we'll discuss the patterns in the next slide. From this sequence, we can find a formula for triangular numbers, which is given as T sub n, which is equal to n times n plus 1 over 2, where Tn is just the nth term or the nth triangle. Okay, so keep in mind as we were working with our triangles here, keep in mind when we're saying nth triangle, we're talking about these triangular numbers and triangles inside the pattern, right? Guys getting the hint? Yes? So Pascal's triangle. So just a little bit, because you guys did ask me for history on Pascal, right? So Pascal was actually named after, I think it was Blaise Pascal in the 17th century. He was both a mathematician and a philosopher. He was not the one who created Pascal's triangle. Even though the triangle was named after him, there were many mathematicians before him that both knew about this triangle and studied it. And, you know, I only have a list of so many, but there's definitely way more out there. There's a Persian mathematician, I think it's Al-Karahi, who worked on this triangle in 953. He kind of also wrote the first descriptive book about the triangle that unfortunately the book got lost. So we don't have any access to what that book was like, but you know.
Al-Kharari, like, it's like with a K or a KH, just think.
Al-Karaji. You know, and there's many other people that worked on this triangle, right? So different formulas have been formed, different patterns. Pascal was the one who took properties of this triangle, properties we already knew about, and he used them to solve probability problems. He also was able to discover other properties by just working with Pascal's triangle, and then even created proofs for them. So he got to do a lot of really cool things.
Did you want to add something, Armand?
I was just gonna say, the Persian polymath you were actually mentioning, he was actually the founder of algebra, and I'm actually Persian, so I know about these facts. And then also something add to Pascal, he's actually originally from France.
Yeah.
Oh, like you mean like Al-Khawarizmi? I mean that one?
Yeah.
That's the founder of algebra.
Yeah, definitely. Yeah, there's French mathematicians that worked on this, Persian, Chinese ones that worked on this. So I think it was Jia Qiang. I only hope I'm saying this right, but Jia Qiang worked on it in the 11th century, and also Yang Hu worked on it also. So there's a lot of different people that got to work on Pascal's triangle. And because we had all those mathematicians, there was a lot of really cool properties and different ways of seeing Pascal triangle. So if you looked at the diagonals, you see all the ones here and all the ones here, right? All of these diagonals right here, all the ones, these are just going to be ones, right? But if we look at the second diagonal here, this is just a number 1 counted on, right? The third diagonal is our triangular numbers. And our fourth diagonal is our tetrahedral numbers. So a lot of little cool things and to learn from the Pascal's triangle. Also, we also can see that it's symmetrical. The numbers on the left side are identically matching the numbers on the right-hand side, kind of like an image, mirrored image, right? Another thing to see is that horizontally, there's sums. 1 is going to give us 1. 1 plus 1 is going to give us 2. 1 plus 2 plus 1 is going to give us 4. 3 plus 3 is 6, plus 2 is going to give us 8. And you can see that horizontally, these are going to be powers of 2. So this is going to be 2 to the power of 0. This will be 2 to the power of 1. This will be 2 to the power of 2, and so forth. And just as we were going over an example with 11 squares, right? This is the same thing as 11 to the power of 0, which is going to be 1. 11 to the power of 1 is 11, right? 11 squared is the number 121. What's another one? 11 to the power of 3 is 1,331. So there's a lot of really cool things you could do with this. Another thing is Fibonacci numbers. How many of you remember what Fibonacci numbers are? Anyone?
I have
Yeah,
a question. Is this what you call like number theory or something?
not necessarily number theory. Well, yes and
Like
no.
like that Indian mathematician like Srinivasa
Ramanujan?
Ramanujan or something.
Yeah. Like Maria said, it's yes and no. So technically, right, all of this is number theory. But as far as, is this what a number theorist would do all day? Not necessarily, just because we've got more complicated stuff now that's built on this and based on this and has kept going. So it's kind of a gray area, sort of, but is it meaningfully number theory? It's hard to say.
But it's definitely really cool to see. You can see here that this 9 plus 1 is 10, 1 plus 8 is 9, 1 plus 7 is 8, 1 plus 6 is 7. You can see a lot of these really fun patterns. 5 plus 10 is 15, 10 plus 10 is 20. And you see a lot of that with Pascal's triangle. And, that's why it's really a famous triangle, because you could just do so much with it.
And there's someone who actually sent a message who was commenting on, this looks palindromic. And
right.
Yes, it does, but just be a little bit careful. If you look at the 1, 2, 3, let's call the top the 0 1. So the 1, 5, 10, 10, 5, 1, that's actually not a palindrome, because you've got 1, 0, 1, 0 in the middle. If you switched it around, you'd have 0, 1, 0, 1. So it's close, but not quite. But there's that type of thing in here.
Does that make sense, everybody? Yes? All right. And there's also just many other different patterns and cool things that come with this triangle, but we're going to move on to the next slide. If you'll have questions as far as this go, or anything more, we can definitely answer them at the end. And in case you're wondering, yes, this is Pascal in both black and white and color. All right. But keep in mind that triangles aren't the only shape we consider in mathematics, especially when it comes to patterns, right? So we can consider really any shape. And so we can have any set of polygonal numbers. Let's do an example. So what about here, right? What do you guys notice about these shapes right here? What's the pattern?
It adds 1 on each side each time.
Okay. Anyone else notice something?
What I notice is that there's each time it starts with 1 circle, and then it goes by 2, and then it goes by 3 on each side, and then 2, 3, 4.
Okay. So here we have what? We have 1, as somebody's already chatted. We have 4. How many we have here? 9 and 16. What do those numbers represent?
Polygonal numbers.
True,
What's the
but what are
word?
these numbers? Yeah, what are these numbers called that you guys called them before, like previous
Quadratic
days?
numbers.
Starts with
Oh,
a
too fancy. Yes, quadratic is true, but what's the simpler word?
Square numbers.
perfect squares, right? So you can see here, definitely we're showing you that triangular numbers are one thing, and here now we have perfect squares, right? So there's different really cool patterns in mathematics and different sets of numbers and that we use.
And notice the names make sense. I think for some of you, you might have gotten used to, oh yeah, a square number, like 2 squared is 4, 3 squared is 9. But they're literally squares, right? There's a reason they're called things. And that's so far, in all the math I've seen, if something has a name, there's a reason it's got that name.
Yeah. All right. So
Not just in math, but in a lot of others. But just a comment.
Yeah, I mean, hopefully, right? Because we don't want to confuse people with what we study. Sometimes you get awkward names, but
I think I found the reason why pi is called pi, because pies are circular, and pi is used to find out pi circumference and area. I mean, it makes sense, even though it's Greek numeral. It's
That's what I was going to say. Like back when the Greeks used that letter, I don't think they used that to represent the food pi. But nonetheless, it's a useful way to remember it.
Well, I mean, you never know if baklava pie is represented by the numeral pi. You never know.
It's true. That's true.
All right. So another thing we'll just discuss before we actually go into the example. What's the difference between triangular and perfect squares? Anyone know? What are some differences that you guys noticed?
I've noticed that triangular numbers are in 3s and squares are in 4s, logically speaking.
Right. So when we talked about the triangular numbers, we can always look to Pascal's formula, Pascal's triangle, and use this formula to find out triangular numbers, right? Whenever we're trying to find a square, we know simply to just square the number, right? Okay.
I wonder how you would read that Tn equals n plus 1 divided by 2 or something.
Well, let's say that n is the number you choose, right? And you want to find a triangular number of, let's say, what is the triangular number of 4? Then n would be 4, right? So the triangular number of 4 is just simply that n, which is 4 times 4 plus 1 all over 2. And I know my 4 looks a little wonky, but we go 4 plus 1, which is 5. 5 times 4 is
20.
there we go. And 20 divided by 2 is
10.
10. So the triangular number for 4 would be 10.
Wait, because it's like kind of like below the 4, right? So then the triangular number for 3 would be 6, I'm just guessing.
And sometimes you don't have
Right.
Pascal's triangle to find this out, right? So that's why we use the formula. That makes sense, everybody? Yeah.
Just to comment on what he was saying, though, that above he had 3 and then 4. Well, that's because that top row is just counting, right? So yeah, the second one is right here, the third one's right here, the fourth one's right here. So that's why that's happening. But that's a good observation.
All right. So here I'm going to have you guys try it out for yourselves. What is the 13th triangular number? And I went ahead and I made sure to put the equation for you guys in case you missed it.
I might be wrong, maybe like 7 or something.
Well, I'm not saying right or wrong, but let's give everybody a chance to answer. Make sure you're chatting either me, Alex, or Connor, preferably Alex and Connor, because they're going to be picking on you guys. So Connor and Alex, whenever you guys feel you are ready to call on someone, go ahead.
Okay. Do you want me to wait just a little bit, or go ahead? I know you just said it, but I'm just checking because it's immediately after you said so. Okay, Jennifer, would you like to share what you got and how?
I got 91, and I followed the formula, and I did 13 plus 1 times 13, and I got 182 divided by 2, and I got 91.
All right, let's slow down a little bit. So what you did was you did the triangular number 13. You went 13 times 13 plus 1 over 2. So 13 times 14 was?
182.
And you divided by 2, which gave you what number?
91.
91. Did everybody get the same, or did anyone get something different?
I got something different.
What'd you get?
I got 78. and I didn't do it your way, but I figured out another way to do it. So you start from 0, right? And you can go all the way up to the 13th triangular number. So like 0 plus 1 is 1, 1 plus 2 is 3. And then you go up and go up until you get to the 13th one, which is 78.
So I think you're off by 1, because if I take 91 and I subtract 13, I get 78. So I think what happened, because you said you start by 0, and actually we don't, we start by 1. So I think that's what happened there.
Does that make sense? Yeah, okay. So how about another practice? What is the 13th square number? I'm not giving you any formula for this one, okay? Does anyone want to share how they solve this one? Jacob, you want to share?
So to find out what's the 13th square number, all you need to do is square it. So 13 squared equals 169.
Did everybody get the same? Would everybody agree? Anyone disagree? Mark, I think your hand's up. What's that?
I thought it a different way. I thought it was like disordered with the equation, so I put like SN, because square number, and then equals to the n parentheses n plus 1, and then parentheses over 2. I got confused.
Okay, yeah. So it was just you use that was the triangle number.
Yeah.
Right, because that was the formula for that.
All right. And you could
However,
definitely... Oh, go ahead.
I was going to say, Mark, I realized you just said you wrote it as SN. So you're ahead of us. Something's coming. There's another thing that triangle numbers are called. That's all I'll say. Maria will get there.
Okay. So definitely think about those rectangles and those squares. I mean, those squares which are rectangles. But when we did the first square, we knew it was 1 squared, so it was 1. When we did the second square, we knew it was 4. So 2 squared, being the second squared, is 4. So when we continue that pattern, we'll see that the 13th square is just simply 13 squared. So it's definitely a fun little question to go in and ask. But let's go on to the next problem. And this is actually quite a popular problem in mathematics. And you'll see a lot of these locker problems with 1 through 10 or 1 through 50, 1 through 100. And then if you really want to be a puzzle maniac, you could do 1 through 1,000 or 1 through 10,000. It's a lot of work, but it could be fun. So here, imagine that you are on school and campus, right? We're back to school. 100 students are going to be assigned for the lockers 1 through 100. The student assigned to locker 1 is going to open all of those lockers. The student assigned to locker 2 is then going to close every other locker. The student assigned to locker 3 changes the status of the lockers whose numbers are multiples of 3. So that means if a locker is a multiple of 3, it is opened, right? If it's open, the student closes it. And same thing, this is going to keep going from the 4th person to the 5th person and so on. But remember, so here, when you do this problem, and I'll give you guys a little bit of time to actually work this out a little bit and see if you could come up with what numbers are, I think the question is asking for opened, right? What's the status for assigned to? Yeah, okay. So here, I want you to think about it, okay? When you walk through the halls, every single student is going to start from the very beginning. So first person is going to open every locker. Second person is going to start from the beginning and open every other locker, and so forth. I get you guys a little bit of time to think about this problem, and then we'll work on it together.
When you say every other locker, are you saying that he will he will close the first locker and then the third locker, or is it that he will close from the second locker?
So I'll help you out with a little part of it. So the first person is going to open every single locker, okay? So all of them are going to be open. The second person is going to come from the beginning. He's going to close every locker, right? Every other locker. So that means he's going to close this one, close that one, close this one, and keep going. So starting every other from the first one he starts. The third student, no problem. The third student is going to go ahead and change the status of the locker for it if there's multiples 3, right? So starting from the beginning, if 3 was open, that means it now becomes closed. If 6 was open or closed, then that status changes. So take a minute or so to work it out, and then we'll go through it together. All right, someone has found an answer. How's everybody else doing so far? Good. I'll wait for a couple more answers and then we'll go over it together.
Okay. Do you want me to call on anyone, or you'll just go right into it?
Just give it another minute. How many of you have seen a problem like this before? Anyone? Okay. All right, so here are all my beautiful lockers, okay? I put them everywhere, so we don't miss a single one, okay? So here, remember that it said, and I know some of you aren't exactly ready, but I'm going to go over it just in case, because I know a few of you are ready and we're going to move a little forward. The first person, locker 1, is going to go ahead and open all of the lockers, right? So locker 1 is going to be open, and so are all of these other lockers, right? The second student is going to what? The second student is going to close every other locker, right? So starting from the beginning, every other locker becomes closed. Got to move the little bar from Zoom. So every other locker becomes closed. So that means all of my evens are closed, right? It's going to take me a little while to write all the C's, but we're definitely going to go through all the little parts here, okay?
Oop, those aren't even.
Oh, whoops. I'm not paying attention. Is it eraser, pen, or eraser? I don't want to erase everything.
You
Oh,
can keep
great
it because
question.
the every 5. Keep it because it's every 5.
Well, when we get to 5, we haven't gotten there yet.
Well, then that would just be inefficient.
Here we go.
Erase it and then just keep it back.
There we go. There we go. That's okay. It's a long problem, so it's okay. So closed, closed, closed. I'll just put a dot. That might be a little faster. Closed, closed, closed here, closed here. So green, I'm using for closed. Does everyone like the green? You see okay with the green?
Yeah, but you might want to erase the green on the 1 if we're using nothing to simplify it open.
Mm-hmm. So here it's open. I'm just going to circle that then. Okay. So here we went ahead. The first student went in, opened all the lockers. The second student went in and closed all the other lockers. Now the third student is just going to change the status of all the lockers that are of a multiple of 3. So that means that if this was, since we're starting at multiples of 3, a multiple of 3 would be 3. Since it's open, it becomes closed. Since 6 is closed, it becomes open. Since 9 is open, it becomes closed. Since 12 is closed, it becomes open. Since 15 is open, it becomes closed. Since 18 is closed, it becomes open. Well, this might be a little better way to do it. Open becomes closed. Closed becomes open. And I got to move all the little video chat openings here, but so here it's closed. Here it's open. Here it's going to be closed. Here it's going to be open. Here it's going to be closed. It's going to be open. Right, that was, yeah, open. Here it's going to be closed. Here it's going to be open. See a little pattern here?
Just a comment, I can see that there's a pattern of closed and opens. That's it.
Mm-hmm. Closed, open, closed, open. We'll get to it real quick. I don't know if I'll complete the whole thing, but we're going to go for up until everybody is good. This one is closed, sorry. Okay, so that was just the first part. The next part, and I'm going to choose a different color for the next one, is now the fourth student is going to do the multiples of 4, right? So we're just going to change the status of all those. So starting from the beginning, well, multiple of 4 is 4, so we go from closed to open. 8, we go from closed to open. 12, we go from open to closed. We go from closed to open. We go from closed to open. From open to closed. And so forth, right? And ask questions if you have questions. And GTAs, if I missed one, because it's super easy for me to make a mistake just like any of you, let me know.
Armand, did you want to add something or comment?
I wanted to say that sequence is dealing with a lot of math, but that's it. Like like what we're doing here, I can see that there's a lot of sequence going on.
Oh, just in general, having sequences. Yeah. Yes. That's partly because of the topic that
Maria.
we're doing with prime numbers and
I missed one.
palindromes.
88, not 89.
88. Oh,
Yeah, because of the topic we're doing. So there's a lot of sequences. So let me think for a moment before I say things that are too drastic. Yeah, I mean, depending what you do, you could probably, if you wanted to be a mathematician and do research, it's entirely possible that all you would deal with all of the time could be sequences, depending on what you picked. It's also possible that you could literally never get a sequence if you picked something else. So it depends what you're studying. But yeah, for this, absolutely.
okay. So we would just keep on going, right? But the first thing I want to just go ahead and point out is that we can see that 1 is open, and so is going to be 4. The next person that's going to come in is going to start from the 5th locker. So 1 and 4 are going to be continuously open, right? Because we're never going back to those numbers. And what someone had mentioned before is if we were to continue this pattern, we'll see that the only numbers that are left open are going to be 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. What do we notice about these numbers that are going to be open at the end?
What about 83, 89, and 97?
Well, I had not finished. I was just saying if we continue our
Oh,
pattern,
okay.
our 5th person, our 6th person, our 7th person, our 8th person,
No,
all
but
the way
those
to
would all
100.
those would be open because they're all prime.
But
So yeah,
They would
someone
go by
else.
4.
But if we
Go
went
ahead.
by 4s and 5s and 6 and we kept going, the numbers that are left open, not necessarily prime.
And go ahead, Erica. I know you had your hand up.
They're all perfect squares.
Right.
Mhm.
So if we
Yes.
continue from the pattern, which by the way, I don't want to do here because it'll take a long time for me to write all those O's and C's and I'll just confuse myself a little bit. But
I do want to mention, because someone said primes, and I actually got a direct message talking about primes as well. So some of you, this looks very similar to something called the sieve of Eratosthenes, a way to find the prime numbers. The thing is, the procedure we're doing here is not the same procedure as you do for that. So it looks similar to the prime number algorithm, but it's not the same as the prime number algorithm. So that's a good thing that it reminds you of that, because it is an algorithm. It's a process to get a certain set of numbers, but this particular one does not give you prime numbers. And something you should think about is, why is that? Why does the other one give us primes, whereas this one gives us perfect squares? And now I'll shut up because Maria's going to go into that.
well, I think you can go ahead into that. I'm going to go on to the next problem, but we could definitely discuss it at the end if you don't want to.
Okay, but we'll leave it there for now, though,
Okay.
unless someone else explicitly wants to ask or add something.
We'll go into actually solving some of these questions, right? So I know you guys did a lot of the work on your own, and I only did it partially. But I'm going to ask which lockers were left open and why were they left open? So as we discussed this, that our lockers that were left open were our numbers 1, 4, 9, 16, 25, our 36, and 49. And these we just discussed in the last slide. So 64, 81, and 100. And that we've established that these are
Perfect squares.
perfect squares, right? What if I was going to ask now, since we know that, which lockers were touched exactly 2 times? And how do you know that these lockers were touched 2 times? Let you guys think about answering that question. Take a minute to decide, and then you can also share your answers with Alex and Connor. And someone had mentioned something a little earlier and kind of hinted at what this could be. Alex, Connor, let me know if you have any answers.
I have someone who asked if they can ask a question. If they mean in the chat box, sure. If they mean their voice, then go ahead and unmute yourself and ask.
I was gonna ask, wouldn't they all be touched twice since the one opened all of them, and the numbers 2 through 5 kind of changed their status?
Well, you have to think about it. So the first person opens all the lockers, right? The second person closes every other, and the third person goes ahead and opens multiples of 3. The fourth person opens multiples of 4, right? So really, when you think about the numbers that are going to be only touched twice, whether it's going to be open and then closed or closed and open, those numbers don't have a lot of multiples, right? Because you don't want them being, touched twice, more than twice, right? So what numbers do you think only get touched once? Think about that, and then think about what numbers get touched only twice.
And just in case this was part of it, remember, we're looking for touched only twice or exactly twice. There are other numbers that get touched a whole lot more, but we're not talking about those. We want only twice. If it's touched 3 times, we're not going to say that it was touched twice.
Mm-hmm.
Excuse me, I think I know the answer.
You want to go ahead and share?
They're primes, because the first person touched all of them, and then it's when it's the prime's turn, it gets touched again.
So what are the primes? Can anyone tell me?
Do you want me to tell you all of the primes from 1 to 100, or the primes?
Yeah,
that
you guys
didn't
got to know
mention?
your primes.
So the primes up to 100 are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37,
I have to slow down.
41. Oh,
Just
sorry.
so that everybody can follow you, and also I can circle them.
Sorry. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61.
Okay, pause for
He's
just a
faster.
second.
He's still faster than me.
Sorry.
Yeah.
I can't write as
Where
fast
did
as
you
you
leave
talk.
off?
All right, I'm
43.
going 43.
So Maria, you missed 29. Go ahead and grab that one.
There we go.
Okay.
Where did you leave off?
49 or 47. Excuse me.
All right.
47.
You won't be able to list all of them because they're infinite.
Well, we're
Up to
only looking
100 it
through
was.
one. Yeah.
Yeah.
Prove it.
But
Just kidding.
53, 59, and 61. 67, 71, and 73. Yeah. And then 79, 83, 89. And then 97.
How many of you have some of these numbers memorized?
Me.
All right. Okay,
I mean,
so
I kind of just listed them off.
yeah, good job. So we know that these are touched only 2 times because they are prime numbers, right? So why do we not use 1 as a prime number? Anyone know?
Go ahead, Erica. Oh,
Because 1 can only be multiplied by itself.
Right.
So it will only be touched once
Right.
at
And
the
then
very beginning.
another thing to keep in mind is the definition of a prime. A prime number is a number that can be multiplied by itself and 1. So since 1 can only be multiplied by 1 and not itself, technically, definition is a little interesting, but 1 would not be considered a prime number. But good job on finding out that these are primes. So you can see the difference from when we were going into our problem in the locker problem that we pointed out all of the squared numbers. And then when we talked about the numbers being touched exactly 2 times, we have prime numbers. So it's really cool and interesting that we got to use the same problem to find 2 different types of patterns. Does that make sense to everybody? Did everybody like this problem? Yeah, some of you like it. Okay. Some of you are like, okay. Did anyone not like this problem? It's okay to be honest. There are some parts of math that it's, it's either you like it or you don't. Or maybe you don't like it because you haven't learned it yet, right?
The only thing I don't like about math is geometry. Just is.
that's okay.
Well, I
More
mean,
for me.
yeah, that's that.
Okay.
Blasphemy.
So let's talk a little bit about prime and composite numbers. Now, what are prime numbers?
Any number that can be multiplied by 1 itself.
Now, is it any number? Or any
Only
natural number?
Any natural number, I guess.
Natural.
So that means natural numbers include even 0, right?
Depends what book you're reading. So what you'll see a lot is people will do an n with a little 0 on the bottom to include it. So it just depends. We can throw 0 in here and this definition is fine because you can't divide by 0. So it wouldn't be a prime because it can't be divided by itself because you can't divide by 0. So you can throw it in there.
Okay. What about a composite number? Anyone know?
Wouldn't those be just like the non-prime numbers?
What's another definition? The natural numbers that what?
Yeah, natural numbers that can be divisible by 1 and another number as well as itself.
A natural number that, and I'm just going to change up what you said by using a couple different words, that has more factors other than 1 and itself, right? All right, good. So everybody knows the definitions, right? And what's an example of a prime number? And how do you know? What's an example of prime? Anyone can give me a prime?
37.
37, because it's multiplied by 1 times 37. What about a composite number? Anyone has an example for a composite number?
36.
Why? Because 36 is?
6 times 6.
6 times 6. What is 36 also?
Do you want me to do like all of
Give me
the
just
six
one more.
factors?
Just give me one more.
Okay, 2 times 17. No, not 17. Something. I've got a giant brain fart, sorry.
You're good.
12 times 3.
12 times 3. Okay, good. All right, so we understand prime and composite numbers, right?
18.
So one method for finding prime numbers is using the sieve of Eratosthenes. I only hope I'm saying some of these names right.
I got you.
Aristophanes.
Eratosthenes, okay.
Yeah.
So here is just kind of an algorithm using, our table of 1 to 100, how we can go ahead and find out those prime. Well, first, we know that 1 is not prime. So that could get crossed out. Then we know that 2 is prime, and we can always cross out any multiples of 2. So we cross out all of these guys right here. Gone, gone, gone. They are all even and multiples of 2, and they are not primes. Next, we circle 3, and then we cancel out any of the multiples of 3. Right? And we can continue to do this, right? And we keep going, and then we do the same thing for 5, we do the same thing for 7, and so on. And this would take some time, but you could definitely do this, and you would just keep on going all the way until you have no more numbers, right? And again, we're going to be left with our prime numbers, which would 2, 3, 5, 7, and so on, as we discussed in the last examples, right? Does that make sense, everybody? So if you ever forgot, if you did not memorize all of the prime numbers, this would be the long way to find them all. Okay? So how many of you want to think about memorizing? No? Yes? It's okay. There's many more things to memorize. Like in geometry, you can memorize the unit circle, which is probably something you definitely want to memorize.
Or pi.
Oh, pi. Okay.
3.1415926.
If you memorize pi, you're going to be memorizing that forever.
I mean, I know like the first like 37 digits, so
there you go.
I'm
Good
chilling
job.
pretty much.
I need to know 47, and you have to know, you have to know a lot more. Maybe you might don't. I'm not trying to be religious here, but I'm not trying to be religious here, but I mean, God knows all the prime numbers and all the numbers in general.
I'm not trying to be religious here. Proceeds to mention God.
Right. So we could just keep on going, right? So just circle and circle and circle, which we did this in the last example where we talked about finding those prime numbers, right? So I'm going to leave this up for you guys, and you guys can play with this chart at home and try to do it out for yourselves, okay? But I want to go ahead and try some examples because I want to hopefully finish today's topic or get through most of today's topic so that next time we can really go into cryptography, which will be a lot of fun. So let's go ahead and discuss the prime factorization of 1400.
And 40.
Oh, yes. 40, sorry. I said it in my head.
That's where it counts, right?
So keep in mind definitions again. This is often a confusion is prime factorizations versus factors. So a lot of confusion is which is which. So when we're saying factors, we're talking about all the numbers that you multiply to make that number. When you talk about the prime factorization, we're talking about breaking down this number into primes.
Like a list of ingredients.
Or a factor tree. And you could probably break this down in multiple ways. So make sure you go ahead and chat to Alex and Connor what you guys get for your prime factorization. And Connor, if you want to pick some students this time, you can go ahead. Has anyone found the prime factorization? Got one hand. Okay. Connor, I don't know if you want to wait another minute or call on students. Up to you.
I've got 2 answers in so far.
Okay.
Maybe just give them a few more seconds.
Okay.
Okay, cool. So I'm just going to call on someone random. And so if you don't have an answer, that's fine. Just let us know. We can pick someone else. So Rachel, do you have an answer that you have that you want to share?
Okay, I got 2 times 2 times 2 times 2 times 2 times 5 times 3 times 3.
You have 5 twos?
Yes, 5 2s.
2 3s and 1 5?
And then 1
Correct.
5.
Is there a way to simplify this a little bit?
I guess you could do 10. Well, I don't.
Well, you can actually go ahead, since there are 2 5s, and I know I make my 2s a little different sometimes. Since there are 2 5s, this is the same as 2 to the power of 5 times
5 twos.
3 to the power of 2, and then times 5. Does that make sense, Rachel? Definitely a little neater, isn't it, to write down? So there's many different ways to go ahead and do this factor tree. And I'm sure some of you probably didn't even use the way that I used. You might have used 2, which is definitely my go-to, especially with bigger numbers. I want to just say it's even. That's the one I know, to divide by 2, right? I'm going to go ahead and use 10 though. And it's okay if you use different numbers. I think you should get the same result. I know that, 10 times 144 is going to give me 1,440. When I take 10, it's the same as 2 times 5. 144 is just the same as 12 times 12. And I could split that a little bit further to make 2 times 6. And then the same thing, 2 times 6. And 6 can also become 2 times 3. And this is how I could do a factor tree, which I'm sure, again, many of you use different numbers, right? But does that make sense, or did anyone have any questions about it? Rachel, you did a really good job. Just, practice on the exponent rules, because that would definitely make your problem a little bit cleaner and easier to work with.
Someone's excited because they did exactly your factor tree.
Exactly. Yeah, it works. But I probably I'm guilty for usually using 2 to start with. But definitely if you use bigger numbers, sometimes it becomes a lot quicker. Like if you were doing some number in the millions, if you use 2, you'll be doing that problem for a long time.
Yeah, but then you'd have to simplify that number down from the millions all the way down to prime numbers.
All right, so it's work.
It still takes the same amount of time.
Yeah. All right, let's go ahead and try some other ones. Anyone could give me the prime factorization of 989. 989. And for those that came in late today, if you haven't had a chance for attendance, could you please just make sure you put your first and last name and hi? So I know we have a couple of people that came in since we began.
Where?
Just in the chat, you can put your first and last name and hi.
It's okay if you privately message us. We'll handle the attendance at the end. Because I noticed a couple of you were a little late, so I just want to make sure that you guys got counted for today. Alex, Connor, just let me know when you guys are ready to call someone.
I'll go ahead and call. Let me do what Connor did and pick someone random. Actually, Alexa H, do you have anything? If not, that's okay.
I'm still working on it.
Okay, that's fine. Let's give everyone just a little bit longer.
I think they have an answer.
Somebody said they have an answer. Did you want to go ahead and answer? Or
Huh? Yeah, just put the answer. Question. I think it is a prime number.
prime number? Okay. You want to share with us?
I don't have an answer, but I think 989 is a prime number.
Oh, I see. I see. Okay. Okay.
Okay.
So
it
we
is
have one
not
vote,
a prime number.
but it's understandable that you would think that.
Can I share my answer for it?
Go ahead.
Okay, so for that one, it's 23 times 43.
Yes. Now, how did you get that?
What I did is basically I divided it into little pieces, or what I also did is try to like find it out a different way, but I divided it. So,
So when you, yeah, can you elaborate what you mean when you say you divided it?
I divided it by prime numbers.
And you just kept going until one worked, right?
Mm-hmm.
Okay.
Yeah, so it definitely becomes difficult to manually check each prime number is a factor until you actually find one. Because once you find one, then your number becomes a little bit simpler. But good job.
Yeah. So this one's different from the previous one because the previous one, there were so many different things you could do, right? There was 10 by 144. You could just start dividing by 2. There were tons of factors. This one was just 2 prime numbers, right? And so there weren't really any tricks. There was just try prime numbers until something works. So that's why it's understandable that one of you thought it was actually prime because like, oh man, 2 doesn't work, 3 doesn't work, 5 doesn't work, 7 doesn't work.
Yeah, so just as Alex will say, it, you know, sometimes you really do have to just test the prime numbers and you don't know, right? Sometimes you have to test everything till you can find out if the number itself is a prime. Okay, so we're going to go ahead. Did anyone have any questions about this or no before we move forward? You can use your mic if you'd like to ask.
Can you ask that? Is there any way besides trial and error to find the factorization?
So I had a hard time hearing you, but are you asking?
Oh, I heard them just fine. They asked,
Okay.
Is there any way aside from trial and error to find the prime factorization?
I only know trial and error. Do you know special trick, Alex?
Not that I can describe. With computers, there are shortcuts, So I'll just say it. Don't worry about catching it or memorizing what's about to come out of my mouth. You can prove that if there is a prime factor of a number, it's going to be less than the square root of this. So this is close to 1,000. So whatever the square root of 1,000 is, you only have to test prime numbers up to that. As soon as you go bigger than that, you know there's not any. So that can save you a lot of work, but you're still doing trial and error for all of those numbers. And the fact that there is no general technique aside from trial and error is why in cryptography, we are so obsessed with prime numbers, which you guys will learn next time.
You should say there's no technique yet.
Yes, fair enough.
Yet.
With the amount of super tasks that we have in quantum AI, then you would think that we would have found something out yet if there was something to find out.
Well, you don't, that's for you guys. We did our part. It's your turn.
Can I say a little bit about history? So,
well, history not till the end. We want to make sure that everybody gets through this topic so that we can jump into another topic.
Okay.
Next time. All right. So when we talk about prime numbers, we know that every prime number can be written as a product of prime factors, right? So, and this product can be found using prime factorization. I'm sorry, not a prime number, a positive number. So question for you all is, what happens if prime factorization is composed of large numbers? I know we talked about it a little bit, but what happens if prime factorization is composed of really large numbers? Clayton, you want to share?
Well, do you mean large prime numbers, or do you just mean like large numbers in general?
Like when I was talking about some number in the millions.
Oh, okay. So essentially, you always want to have your numbers simplified down to primes. So let's say you're working with, I don't know, like 2 million. You could say, oh yeah, well, it's 1 million times 2. Okay, so now your 2's prime, but your million isn't. So you have to simplify that down more and more and more and more.
Right. So it definitely becomes
primes.
It definitely becomes time consuming, right? So as the numbers get larger, when we try to find prime factorization, some of the work becomes longer and more time consuming, right? And it could be really, really hard to manually find some of these numbers. So like our number 989 that we did in the last example, if you had a number that looked prime and it was really, really large, imagine having to go through all the prime numbers to figure out if there's any factors. It's definitely difficult to do until you actually find one. Just because it is time consuming.
Unless you tell an AI to do it, then you could do it in like minutes tops.
But does that help you learn how to do it?
I mean, if you know how to do it in concept, what prevents you from upscaling it? Like, if you know how to build, if you know how to do algebra with normal numbers, and what prevents you from doing it with more complex numbers, like 1 plus 1 equals 2. Yeah, okay, now 13 plus 1 equals 14, so you still know the concepts.
Right, so there's definitely a lot to do. And like Alex was mentioning, we could use the method with the square root, right? That would kind of hint towards what kind of numbers we can use and definitely make our problem a little bit easier. So when we talk about more about just prime numbers, there's different vocab that goes along with that, right? So one method that we use is Fermat's factorization method, which we were already kind of using in the factor tree, right? Another way, another thing that we could learn is about difference of squares. How many of you know difference of squares? How many of you don't? It's familiar? Raise hands. I can see some faces. Yes, you know. Yes, yes. No one's raising hands. I don't know if anybody knows. All right.
I know the basic concept.
Basic concepts, right? So difference of squares is just if we have, let's say, an A and a B, and A and B is just some letters that we're using to represent some numbers. So they're not actual anything other than that. So if you have some difference of squares in the form of A squared minus B squared, then that can be rewritten as A plus B times A minus B. Does that make sense to everybody? Yes? No? All right, write in the chat, yes or no. I need to know from a couple of you. Got to participate. Yes? Awesome. Awesome. So if we were going to use difference of squares, let's go ahead and evaluate these problems right here using that formula, right? And go ahead and make sure you're writing your answers. If you're trying to do this part, make sure you send that part to Alex. If you're trying to do this part, which I'll just call B, make sure you're sending that to Connor. Send this answer to Alex. Send this answer to Connor. Alex, Connor, I'm just going to wait on whenever you're ready.
Okay, I'll go ahead and call on Ethan to go ahead and share your answer and how you got it.
I got 9 because it's 5 plus 4 times 5 minus 4. 5 plus 4 is 9. 5 minus 4 is 1. So 9 times 1 is 9.
Good job. All right, Connor, you got anyone for the second one?
Yeah, Jennifer, do you want to take it away?
Okay, so I didn't do it the same like the formula. I just did it 12 times 12 is 144 minus 25, which is 5 times 5, and then got the answer of 119.
All right, good. So again, just in mathematics, there are multiple ways of solving a problem. Just keep in mind when you do have difference of squares, sometimes it is helpful with those really, really large numbers to split it out just to make sure you're also double checking your work. But yeah, good job with that answer. So it could be 12 minus 5 times 12 plus 5. And that is going to give us 7 times, and a dot for multiplication or a little x for multiplication is just the same thing. 7 times 17, which is 119. So good job, everybody. And I'm super happy about all of you guys participating today, being Saturday and all. Got to do some fun math on Saturday. It's my favorite thing on the weekend. But we're going to go ahead and end for today's session. We got most of this topic finished up, so we're going to just end it next time and go right into cryptography, which is going to be an absolute blast. But before anybody goes, please make sure that you are writing in the chat your first and last name and say bye and have a wonderful weekend. And happy Valentine's Day if you celebrate it. If not, happy Sunday. And if anyone had any